Oh, you want me to do here? Wonderful. That's okay. Very good. Intrinsic threshold stress intensity range and near tip residual stress. And this is tested in the lab in air and vacuum. This is a novel actually test method is now actually proposed as a standard for the ASTM in the USA. He was actually telling me yesterday it's almost reached a very advanced stage. His entrepreneurial instinct has actually made him start actually made in India what we now call as Atmanirbhar. It's a digital test controller, actually along with other colleagues for the universal test machines. He established BIS, Bangalore Integrated System Solution, in 1992. It has done such a revolution in this country. He is supposed to have almost supplied about 7 billion rupees of test equipment to customers for a variety of applications, which included strength, durability, and performance of materials and components. He has actually retired from there, I say, but still actually working around at a very higher level. He contributed to this setting up of BIS-IAST Center of Excellence at the IASC. He is a founding member of Structural Integrity Society. He is an office bearer in its formative years. He contributed to the growth of the president, continues to be its support activities. He was also the third president of INSYS. It gives me indeed a great pleasure to invite Dr. Sundar to come and present his recent work in this field.
science-based and not knowledge-based by trial and error, or shall we say a correlation. And it's really probably unfortunate, perhaps, to everything you have to pay a price. And even though he was an outstanding researcher in metal fatigue at the California Institute of Technology, and you can see him there holding a cup of broken lead circles on the right. Those concentric circles mark interfacial tracking between secondary particulates and the matrix. And they were identical. So that was the history. How did that be? While the main track was going with obvious difference in the track extension of the three different steps. So that was when the idea came upon us, a very memorable experience, that perhaps the mean stress effect has to do with the environment. That it is not just track motion, there is another actor who plays a big role. And that would have to be an even bigger role when it comes to the fatigue limit, because when the tracks is just starting to grow, they can't be any track motion. By definition, you don't have a track, you don't have a motion, and yet the mean stress effect is there. So, again, thanks to the consideration shown by the Air Force lab, I was able to get back to base a year later, and on a very expensive test system at very high levels of vacuum over a period of 1 month. Next slide, please. Next slide, please. You can see on the left the results from that experiment which lasted a month, because we applied a number of blocks of this loading that you see on the top left in air, and then we evacuated the chamber. It used to take 2 days to evacuate the chamber, and applied the next number of blocks in high vacuum, and then release air back into the chamber, continue the experiment till the specimen failed, because we were looking at natural transformation. And lo and behold, you can see, if you look at the middle picture at the top, block 7 was air, block 8 was high vacuum. And you can see in high vacuum, the mean stress effect simply disappears. So that was the final proof that we had figured out what Manson had hoped would be done in 25 years. We had done it a little earlier. Now, as researchers, you can write some papers about this and be happy about it. But I was already an entrepreneur, and I was wondering, from where can I take this forward? Go forward and explain mechanical property, and there's more of physics and chemistry involved in practice. Now, okay, we have a test method now. It's a new method. That method, again, can end up as a paper, but This is a turning point in research on metal fatigue, because finally we got a handle on how and I must tell you, that experience has been overwhelming. Next slide, please. You can see on the left 3 sets of data points which relate threshold stress intensity range to near-tip residual stress plotted on the horizontal axis. These data points were obtained by 14 different labs in 3 countries. And when I reported these results at the ASTM meetings in spring, one of the veterans over there, he asked me, how on earth did you manage to pull off this massive validation? And the answer lies in the enormous support that we enjoyed in this process, without which we would not have been able to do this work. Because each of these readouts that you see on the screen, it took about 3 million load cycles and involved a total of 15,000 hours of testing. The American Society for Testing and Materials assigned it a number, 1866. That study is complete, and very importantly, because of the science behind the method, we are able to translate the data on the left to relationships on the right, which engineers can use, which researchers can use, as a relationship between threshold property of a material and applied stress ratio. This study, is a supreme example of voluntary participation, of selfless support of people around the world. And I could spend a lot of time just describing how much help we got from a lot of people in India, in Russia, and in the US. One of the participants was VNIT, and I'm really glad that we're having this conference here. And I deeply appreciate Professor Peshwe, Atul, for the help that you gave in participating in this, because each participant was given 2 materials to test, and everyone did an outstanding job. Now, the dots on the map over here, they tell you where the labs were located. In India, in Russia, and the FOS lab in the US. All that work had to be technically coordinated, and the Indian Structural Integrity Society played a huge role. I deeply appreciate Professor Vikram Jairam, who is here, who did a lot of the coordinating effort among the participants. We organized workshops which were hosted by the Indian Institute of Science in Bangalore. But if you want to name one team that contributed enormously for this effort, that was my own team in the company. And that's our team. Not all of them, of course, could do this because then we would have gone out of business. But the tech support team from BIS was responsible to make sure that everybody got their specimens, their fixtures, their calibrations done, the software installed, and this is a huge amount of work. But amazingly, there is a connection between this team and Dr. Valluri. And the connection is that he might have actually inadvertently planted the seed for our team way back in 1982, which goes back so many years, more than 40 years. In 1982,
we already had about a year's experience of working with imported test equipment. And with my background, having studied in the Soviet Union, where you were taught, that you can do a lot of things by yourself, and not just in your field of specialization, but in any field that you choose to work on. Even though I was educated as an aeronautical engineer, I went up to Dr. Valluri and told him, Dr. Valluri, we can develop this kind of controller to control testing machines. And he sent I had a tremendous ambition at the time. I told him, this is, the 80s, early 80s. We had 8-bit processors at that time. And I told him, sir, I want to make a controller on one printed circuit board. Just one board, it should control the machine, communicate with the computer, and perform testing of any kind. And he, as a manager, not as a researcher, he was a firm believer in self-reliance. And every time we used to go to him to ask for anything, he'd say, hey, you guys can do it yourself. Why do you want to buy it? Why do you want to import it? This is pretty straightforward. And then he will cite some story from Caltech and say that that's how we were brought up and you guys can do it. So this is how I challenged him and said, I want to do this. And he said, okay, we have to send your proposal to the systems engineering division and see if their head also believes that you can do it. Unfortunately, the head of the division, Dr. Srinivasan, he said, sir, we have never developed a motherboard in our division at any time. But if this guy can do it, it would be a first for the lab. Perhaps he meant it as a challenge, but we got the signature and the precious 3 lakhs to take off on this project. And what you see on the right is the board, the single board that goes as a module on a conventional analog test controller to convert it into a fully automated test system. And again, as our luck should have it, the LCA program took off in 1983. And Dr. Valluri, sure to remember whatever he did, came back and he said, I want Indian materials to go on the LCA, but they have to be type certified, which means that they have to be certified for use on aircraft. So, will your lab be willing to take up that process? And we agreed. It was a kind of not a very comfortable situation. It was a controversial situation because here ADA is giving us 1.5 crores to set up a lab with 5 machines to do type certification testing. And all my colleagues, I'm sorry to say, scientists, colleagues in my group, they went to the director, Professor Narasimha, and moved to another division. They said, we want to do serious science, not some contract testing for somebody. And I firmly believe that you can do a lot of science in industrial work. And this was hardcore industrial work to get materials certified for use on aircraft. And I had learned my lessons in the Air Force lab in the US. If you go to the Air Force lab in the US, you'll find the majority of people who work there are on-site contractors. They're not employees of the government. So I got approvals from the director to set up an on-site contractorship. And I had the benefit of an energetic, little bit volatile, but extremely, active and loyal PhD student who is also sitting right here. He happens to be the president of INSYS today. And we struck a deal. I told him, Raghu, you take care of the type certification testing, design the specimens, have them fabricated, train the technicians to work on the machines, and I'll take care of your PhD degree. Don't worry about that. And I think we both learned a tremendous deal from that. We had a postdoc from the Soviet Union. He is today the Ukraine. And believe me, for the first time in our history in NAL, We had almost, half a dozen publications which came out in ASTM STPs, which was a very difficult place to publish any serious research work. So that goes to tell you how much you can do collaborating with industry, working on practical problems, and still pursue whatever you want to do in academy, in terms of academic pursuits. So we had this battery of machines, and by the way, we did a lot of work, I'm sure Raghu will remember, on L168, which came from here, from the Ambajari plant, for type certification. We also did type certification work. I remember Prakash used to come and ask questions from ADA, along with Mr. Sridhar Murthy. Interestingly, one of the youngsters who took charge of the contractorship, they were all my project students from local colleges. So I told them to set up their own company, and perhaps they were my guinea pigs so that I could go and set up my own company afterwards. Because these guys then became the chap who started the on-site contractorship. He became a kind of a mini Bill Gates in Bangalore. He became a local oligarch in IT. And I think that was the exposure because of working with government. He got some licenses. So his entrepreneurship really took off. And this was a tremendous experience, and I want to cite it today because this was not the time when people knew the word startups. This is all new jargon that we're hearing today, of incubation of startups and things like that. But this took off, and it took off in hardware. The controller itself made its way also into an ASTM STP, and for us it was a great honor that the picture of our single print, single board control system appeared on the cover of that ASTM publication, which contained all the papers that were presented at an automation symposium. And I think that tells you how much you can move forward in problems related to structural integrity, working with industry in a way that you cannot possibly do in many other areas. The company that was set up in 1992 went on to do a tremendous amount of development work in a variety of test systems. I've just highlighted 3 of them over here because they are of particular interest probably to some of you. The exercise itself would not have been possible without the support that we enjoyed from most of the people that we worked with. Unfortunately, many people would tell me, servo hydraulics, computer control, it has to be imported, don't get involved with this kind of thing, just go and do something, at your level. Don't come and talk to us about thermomechanical fatigue, testing, about shake tables. This is not for you. This is for those 1 of 4 or 5 companies in the world. Only they can do it. And we only trust one of them, so we're going to work with them. That was the approach I would hear. But that was not the approach I would hear if I went to the Indian Institute of Science and talked with Professor Dattaguru or Professor Iyengar or somebody like that. They really encouraged us. And therefore, I think, if our company did well, we owe a tremendous deal to the Indian Institute of Science, which now has about more than 30 of our test equipment in different departments. I don't believe that without their help, we would have gone very far in our growth. Not only in technical areas, but even in certain other areas related to the authorities, the tax authorities, and so on. Next slide, please. So here you can see a video of the shake table. That is a 3-axis 6-degree of freedom shake table, which was first installed at the Indian Institute of Science back in 2003, I think. That table was developed for educational purposes, but it served as a huge political statement because at that time it was believed that you cannot do this stuff in India. So we are very grateful to IASIP to give us that faith, to have that trust that we could do it. Today, Indian colleges are better equipped to do earthquake simulation testing than their counterparts in any other country, because here these tables are affordable. They are not in other countries. So we have colleges in India which have 3-axis shake tables for seismic studies. That's amazing stuff. On the, could you just, this is a thermomechanical fatigue test system, which is a very complicated system, it would appear. It's a technological challenge, because you have to heat the specimen but compensate for thermal strain in real time, several thousand times a second, so that you can simulate exactly just the mechanical component of strain in testing. There are hardly 4 or 5 companies in the world who offer this equipment. And this was an item that our nuclear research establishment could not get for love or for money. Not anymore. In fact, we have a foreign company which has about half a dozen of these systems, which is procured from us. And I believe that the development of this technology in the country went a long way in the technology being opened up elsewhere. On the left, go back please, go back one slide. Back one slide. Yeah. On the left, you see, unfortunately, the video is, it's rotated 90 degrees, but that's a test system, a triaxial test system to test turbofan blades on commercial aero engines. And I believe that it's one of a kind. And we built this for an aero engine, commercial aero engine manufacturer in Russia. So obviously, if we can support technology development in other countries, we can certainly do it back home as well. And you look at that team sitting there of youngsters, you wonder how they can do it, but it all can be done. This is possibly the most impactful thing we have done, though it has very little to do with science and very little to do with the technologies of structural integrity. This is a shock absorber test system. Why do I consider this to be the most impactful thing that we've done? That is because 3 million shock absorbers go through our machines in India before they are packed and sent to automotive manufacturers, whether it's a 2-wheeler, 3-wheeler, 4-wheeler, railway wagons, locomotives, doesn't matter. Chances are, if you are riding a 2-wheeler or a 4-wheeler, your shock absorber spent a couple of seconds on our machine. And I think that's a matter of great pride, because that increased the quality of Indian shock absorbers to the 6 sigma level, which would not be possible unless every part is tested. And if you're going to test every part on an expensive imported machine, your business isn't going to be competitive. That is the equation. So we have to focus on technology development. Next slide. We've supplied a lot of equipment to Russia. It's a matter of great pride for me that the trains in the Moscow metro, their parts are tested on our equipment. The escalator steps on their hundreds of kilometers of escalators in different metro stations, they are tested on our equipment. And on the left you can see pictures from our lab as a private lab without a cent of public money, without borrowing anything from government, without a grant. We set up the largest private lab in the country, which is the only lab that is NADCAP certified for both metals and composites. So therefore, we are able to undertake a lot of contract testing for the aerospace multinationals and for DRDO. And I believe that our lab is a huge successful platform for our own young engineers to learn. And I take great pride in the fact that we take in interns. We love to have students. We have had a lot of students from overseas who come to do their experiments for their masters, for their PhD, and they learn a lot about test equipment as well. When we started the lab, the idea was that we should first produce defects that our customers are likely to see later on, so that they are, the burden they face is reduced. Next slide. This is a very memorable picture of Dr. Valluri at the first SICE conference, where my colleague Dr. Murli Mohan is explaining to him the operation of a scanner which we developed to look at defects developing in the course of testing. So this is a scanner that works during the test, and Dr. Valluri was our guest of honor at the SICE 2016. Vikram will probably remember that, and Raghu. He was already past 90, and I think we were very lucky to have him come over and spend a few minutes with us. Next slide. This is a picture which you wouldn't associate with a meeting like this. I just picked this out of the internet a couple of days ago, and this is about you know that the gap between the rich and the poor is increasing by the week, and so those few who are extremely rich, they are willing to invest on prolonging their life. So the life extension program for individuals is on, and it's a very attractive business in the Emirates. You can go to the 100th floor and swim on the pool over there and look at Dubai, and it's a business proposition to get into life extension programs for very rich people who can afford it. But next slide. The life extension programs on our national assets, they can give you infinitely greater returns. Infinitely greater returns. I've just mentioned a few here. Look at the bridges. Civil engineering department in the institute was working on railway bridges some years ago, I remember. There must be easily more than 1,000 bridges built in British times that have continued to be used, and there are discussions about how to extend their life. Look at the railways, the rolling stock, the rails themselves, the nuclear, thermal, power, energy sectors, petrochemical plants. Everything requires life extension. It requires life extension because that is not what the guy who put it in place would be very worried about. Manufacturers want their products to last till the warranty period is over. It's then the onus is on the owner to extend the life. Therefore, this is a huge opportunity because the people who own the assets, they are not experts in structural integrity. They know how to use their assets. They don't know how to extend their life. And this is a huge business opportunity for the structural integrity community. And I think, let me just cite one example next. This is an amazing piece of equipment that we developed in our company for the Department of Atomic Energy, for BRC. What you're seeing is a seemingly unbelievable sight. What you're seeing is a through crack in a pipe subject to cyclic internal pressure. Can you imagine a through crack growing in a pressure vessel and there's nothing leaking out of it? So we developed the technology to make that possible. And based on this technology, the zirconium niobium pipes which carry the primary coolant and the fuel element in our nuclear power reactors, they are being tested for residual strength. But the science of it comes from the fact that on this rig, we got the world's first published results on J1C test on a pressure vessel with a through crack, which was, at that time, it was something unbelievable. In fact, I remember meeting Jim Newman, a close friend and probably the world's top expert in fracture mechanics, who developed all the equations to calculate the crack size from compliance. And he had developed the equation for a through crack in a pressure vessel as well. So I told him, Jim, we confirmed your equation works. And he said, how did you do it? It can't be done. I said, well, we did it. So there is a lot of science and technology, and you can write a lot of papers. Next slide. This is the full-scale test facilities that were started in NAL. at the instance of Dr. Valluri. But these are projects, they go on for several years. The challenge before our community is how to convert this into products so that legal entities by way of private companies, government companies, joint ventures can offer these at a space and time which is an order of magnitude faster than a research lab can do. Next slide. And the best example of a target project is probably the SU-30 fleet, of which we have almost 300 aircraft in the country, which are expected to serve for the next 20 to 30 years. I just made these rudimentary calculations, and if I was a little younger, I'd probably start a company doing this. Next slide. This is an interdisciplinary activity. It involves a lot of disciplines, and one of them is definitely digital twin development. And last night, next slide please, I dreamt that at the 2029 ASIP conference in the US, there is a paper by two authors from Nagpur, Squad Leader Malkiyat Singh from the Maintenance Command and Professor Sushant Thakur, who had started his own incubated unit here at JNIT, and he was doing very well. Malkiyat was his PhD student, and they were presenting this work at the ASIP conference in the US. Given the title of the conference involving a top-end Russian aircraft, you can imagine all the panel sessions were closed and everybody was sitting at this session listening to what Malkiyat had to describe about digital twin development for the SU-30. So that was a dream I had last night. Next slide. When Dr. Valluri, in his book, he writes, many of the faculty members at Caltech, they used to create terror for the students the next day after visiting local industries. And that was because they used to come back with practical problems for coursework. And it seems to me that that is a kind of bridge we need to build with industries around us, so that we can make education practically useful for the students after they graduate. Next slide. I'd like to conclude. I think I've taken more time than I should, with a slide showing the title of the book that Dr. Valluri wrote. And he mentions in the book that our ability to defend our skies in times of war cannot and should not be mortgaged to other countries. So this is the message that should inspire a lot of our young engineers, scientists, to not just stick with their paper writing, but get into something that is rewarding, both materially as well as intellectually. Thank you very much for your time. I apologize if I've taken more time than I should.
In the area of the fatigue, fracture and the structural integrity, Dr. Sundar and his colleagues at NAL have done outstanding work. So many people abroad, when I go, they actually murmur in my hand, you know who is the best fatigue scientist in your country? I tell them I know. So please hear him for the very outstanding lecture. Please. I hand over to the President, Raghu Prakash. Usually in the memorial lecture there are no
Dr. Sundar for a wonderful memorial lecture that should be and should have been. So I request Dattaguru sir to felicitate Dr. Sundar with our traditional way of felicitating a truly good speaker and has been the expert for so many years, and present him with the certificate of the first Valluri Memorial Lecture. Thank you, Professor Dattaguru. Now, as a guru of so many present over here, Professor Dattaguru needs to be felicitated, and no better person to have INSIS President felicitating him. So, request Professor Raghu to felicitate Professor Dattaguru. Thank you, Professor Raghu. So moving on to next session, we are running late by a good amount of time. So I request Professor Raghu to take charge of the proceedings and chair the next session involving two lectures. One is the first plenary of the SICE 2024. So I request Professor Raghu to conduct the proceedings from here.
Thank you. We have two lectures now. One is by Dr. Andy Rosenberger, and then there is one by Dr. B.K. Datta from the HBNI BRC. So the first lecture will be by Andy Rosenberger, and he is going to talk about the aircraft structural integrity program which is practiced in the United States. I now request Andy to come to the stage and deliver his lecture. For the want of time, and I'm not going into the details of introducing the speaker, please excuse me for that.
Right, well, we'll get the charts up soon enough, but my name is Andy Rosenberger. I'm with the Air Force Research Lab, Materials and Manufacturing Directorate. I'm so happy to be here and so honored to be here. This is a great conclave of fatigue and fracture structural integrity experts. I'm hoping to kind of set the stage today for what structural integrity means to the U.S. Air Force and give you some ideas of where we want to go in the future, what our dreams are for what the future of structural integrity will look like. So if we go to the next chart, it's just an outline. It says I'm going to talk about the history of ASIP, the Airframe Structural Integrity Program, NSIP, the Engine Structural Integrity Program, and then talk about the future. That's me up there. Anyone know a good joke?
Yeah,
Can we go to about slide 3? Okay, so it was interesting when I was looking at where structural integrity came from in the Air Force. I found a definition from 1956. Now, structural integrity is that property of an airframe to withstand the loads for which it was designed. And you can replace airframe with anything, right? Structural integrity is making sure that your structure does what it was meant to do. And that's what we were talking about. That's what we tried to ensure for the U.S. Air Force, that we could ensure the structural integrity of our airframes and our turbine engines. Next chart, please. So, the Aircraft Structural Integrity Program, or ASIP. Next chart. So, if you look at how the Air Force was flying aircraft, in World War II, we didn't have a lot of structural integrity problems. Our fighters were not lasting long, they were wearing out. B-17s were getting shot down all over Europe. The only aircraft that saw full life fatigue was our trainers. So that aircraft on the right, the AT-6, that was the only aircraft that actually saw fatigue damage, and that was the first example of a fatigue assessment for an U.S. Air Force aircraft. And that was done at Wright Field in 1945. That's where I work now, is at Wright-Patterson Air Force Base. And they had these 5 safety factors, things you have to consider when you're designing an aircraft, when you're ensuring the structural integrity. So what are your loads? How well do you know them? What are your inaccuracies in your analysis? Where are the errors in your structural analysis? How mature is your material? How variable are the material properties? So you have to well characterize your material. How does the structure